We're continuing the discussion from the last class, and we saw about this problem of what we call by an overestimation of an experiment or underestimation. And so this is one of the other question that I could actually talk about for the latent heat of vaporization of stuffs. Number 6 is actually pretty simple. So I'm going to go by number 7. Why do we have two different power of data? Did I discuss about this question? One. Does anyone remember? Why do we have two different rate of power? I think I did that. Worksheet question number 9. It's about thermometer. So have a look at the question. The question says the resistance of a thermistor at 0 degrees Celsius is 3840 ohm. At 100 degrees Celsius, the resistor is 190 ohm. When the thermistor is placed in water at a particular constant temperature, its resistance is 2300 ohm. Assuming that the resistance of the thermistor varies linearly with temperature, calculate the temperature of the water. This is actually pretty simple. What we have is, in this case, we are provided with the temperature of two different scenarios. So at 0 degrees Celsius temperature, we have the resistance that is 3840 ohm. Then at 100 degrees Celsius, we have the temperature that is 190 ohm. And we are asked, we are given that is at a certain unknown temperature when the resistance is 2300 ohm, which falls somewhere in between through this scale. What is the temperature? So let's say that would be theta degrees Celsius. These are unknown. So as the equation for thermodynamic of thermometry dictates that any amount of change of temperature, delta theta, should be directly proportional to any amount of change of relevant amount of change of thermometric property, which in this case is the resistance of the thermistor. So we can actually write that the delta theta is proportional to delta x. So we can write that one set of delta theta 1 divided by, let's say, delta theta 2 should be equals to delta x1 divided by delta x2. So we are just making this into a proportionality equation while getting rid of the constant that might exist over here, which then can be rewritten into a convenient fashion. So let's say in the top part for the temperature difference, we're going to write theta minus 0. And we should also write the relevant resistances for those temperature values. For the unknown temperature, resistance was 2300. For the 0 degrees Celsius, the temperature was 3840. Don't bother for the big or small value. If you are placing the numbers correctly, your equation will take care of the minus sign. So you don't have to bother about that. On the lower side, we can write 100 minus 0 and place the relevant resistance value of those temperatures. 190, which was for 190 ohm, which was for 100 degrees Celsius from here, from this information, minus 3840. That is the resistance at 0 degrees Celsius. Solve this equation to find the value of theta. দেখা তো কত আসে?
Sir, 42.19.
আমাদের 32.33 আসতেছে।
স্যার আমারও 42.19 এসেছে।
দাঁড়াও দেখি আমি তাহলে কোথাও ভুল করছি, 1 মিনিট। 2300, আচ্ছা হ্যাঁ, আমি 3840 কে ক্যালকুলেটরে 3480 লিখছি। Yep. হ্যাঁ ঠিক আছে, 42.19. So this temperature is gonna be 42.19 degrees Celsius, or you can write in 2SF 42 degrees Celsius, just get rid of this thing, or 3SF 42.2 degrees Celsius also acceptable. Just a quick refresh of the memory for the thermometric equation that we learned in our O-level syllabus. Number 2 says the temperature of the water as measured on the thermodynamic scale of temperature is 286 Kelvin. By reference to what is meant by the thermodynamic scale of temperature, comment on your answer in 1. So this can prove to be a bit of a challenging type of question because it is actually quite rare. They say that by reference to what is meant by the thermodynamic scale of temperature. So within your answer, and this is a 3-mark question, important fact, within your answer you have to define the thermodynamic scale of temperature, or Kelvin temperature scale appropriately, and then you have to make some comments of this calculation right over here, and be able to use that relationship over here for the math. So somehow you have to use your definition that you're going to be using to explain thermodynamic scale temperature. You have to use that definition to make a comment about the process that you achieved or did right over here. So how could this work? Let's look at the mark scheme and try to find out what kind of wording does the examiners want. First, we have to define the Kelvin scale, and then we have to use the Kelvin scale definition to make some comment about this temperature. So that's what we are trying to do. We go by for the mark scheme. This is question number 9, A2. It says 286 Kelvin is equivalent to 13 degrees Celsius, or 40 degrees Celsius is equivalent to 315 Kelvin. So they just give us a certain conversion. Thermodynamic scale does not depend on the property of a substance. Yes. So change in resistance or thermistor with temperature is non-linear. What does that mean? Oh, I see. Acha. I get what they are up to. Okay, I'll explain. What I did for question number 9A1. First of all, let's go for the definition. The definition should be pretty self-explanatory. We discussed about the definition of thermodynamic scale for the first parts of our class. Do I have it? আচ্ছা, সেটা হচ্ছে thermodynamic scale of temperature, or Kelvin scale of Kelvin scale is defined in a way that includes necessarily that the temperature scale should not be dependable upon the any physical property of any object. It is a temperature that is not dependent on objects, because it is dependent upon, it is defined using the concept of the total amount of internal energy or kinetic energy stored within a certain object. Now, ideally, at 0 Kelvin, object lose all of their kinetic energy, which is what we define as 0 Kelvin. And as object goes, as temperature goes up, object has more kinetic energy within themselves. So if you try to get a bit of a difference, for example, degree Celsius scale was actually defined using the properties of pure water under 1 atmospheric pressure. So a certain specific physical substance is required if we want to recreate this scale from scratch. From scratch means this, so we do not have any thermometer, but we want to be able to create a thermometer that reads the temperature at degree Celsius scale. Then we would require, necessarily would require to have access with to pure water if we want to recreate that scale. But for Kelvin scale, we do not need that as a compulsion. It would be helpful, but we don't essentially need it. We have to have it. There's no such thing. Similarly, if you think for Fahrenheit scale, we don't use it in physics almost at all. We don't do that, but in biology, or we still have some use for it. In the Fahrenheit scale was actually derived upon the temperature of a type of alcohol, ethyl alcohol. So the 0 Celsius in Fahrenheit scale was actually the boiling temperature of the alcohol, and the 180 Fahrenheit was the melting point. Sorry, I mean, it was based upon some specific type of alcohol, most likely ethyl alcohol, as far as I remember. So that's the basic idea behind thermodynamic scale of temperature, that it is not exclusively dependent on any physical object. And for the other part, by reference to what is meant by thermodynamic scale of temperature, comment on your answer in one. What this part requires, actually, I misread the question and did the math all right, because my approach was okay. Have a look. This question did not say that, assuming that the resistance of the thermometer varies linearly with temperature. Have a look at this thing. I assume that they were saying this, that the change of temperature is directly proportional to the change of thermodynamic property, but they didn't actually say that. Specifically, they are saying the resistance of the thermometer varies linearly with temperature. So what they proposed within the question is that theta proportional to R. That's what they proposed, which should lead to theta 1 by theta 2 equals to R1 by R2. So yeah, so what would be a problem? What did they get? 286. 286 Kelvin করতে আসছে। I'm not getting this question anyway. এটা কি হইলো? মার্সিম এখানে একটা টেম্পারেচার মেনশন করা আছে, either 286 Kelvin is equivalent to 13 degrees Celsius or 42 degrees Celsius is equivalent to 315 Kelvin. Where is they getting this 286 Kelvin from? I mean, 13 degrees Celsius is coming from which calculation? Or 286 Kelvin is coming from which calculation? Ah, I forgot the first sentence. Got it. Okay. Here is the stuff. The question says the temperature of the water as measured on the thermodynamic scale of temperature is 286 Kelvin. This is already provided to us. By reference to what is meant by thermodynamic scale of temperature, comment on answer in one. So what we're getting that if the question has already told us that the Kelvin temperature of this water at this 2300 ohm relevant temperature is 286 Kelvin. So if we actually get 286 Kelvin in degrees Celsius equivalency, this should be 286 minus 273. About for 3s 273 is all right, which gives us 13 degrees Celsius. This should be that. So the conversion of this temperature in degrees Celsius gives us 13 degrees Celsius, whereas the actual temperature measured was 42 degrees Celsius. So you can either show this conversion or vice versa. You could convert this thing into Kelvin and show that that temperature, which is about, as the Maxim says, which is about 315 Kelvin, 315 Kelvin, this is also not okay with this temperature. So if we do the numerical conversion of the degrees Celsius temperature calculated into its Kelvin equivalent form, thermodynamic temperature scale, we find that the two answers are mismatching. What could be a possible explanation for this? The most likely common explanation is that the scale is actually non-linear. The scale being non-linear means that we considered delta x over delta theta r over theta, where theta starting from 0. As per the question, this line is supposed to be a straight line. At 0 degrees Celsius, we do have some resistance. We have 3840. So close to 0 degrees Celsius, we have a high resistance, and at let's say 100 degrees Celsius, we have a bit low resistance. So the question assumes that the question assumes that this one is supposed to become a straight line between the two temperature scales that we have. So by calculation, considering this whole line relationship as a straight line, we found out that the temperature which was responsible for 2300 ohm was about 42 degrees Celsius. This is what we did calculate out. But the actual thermodynamic scale temperature, which is considered to be more appropriate or more correct compared to any other temperature scale, because that is defined as the absolute scale of temperature, that scale gives us that the relevant ohms in Kelvin scale was supposed to be only 13 degrees Celsius. So it should be pretty close over here. So that goes on to show that assuming the relationship was actually a straight line shouldn't be actually correct, because this 2300 ohm resistance might as well be somewhere over here, which obviously proves that this line that we consider to be a straight line, which actually ultimately gave us this value, is actually not correct. If I try to give it a bit of a plotting, it might actually look like this. It's supposed to be negative exponential, something like that. So you have a significant high drop at the beginning, or a steeper gradient at the beginning, and then you have a decreasing gradient at the end. So that's why we have the mismatching value of the temperature. But definitely we are considering the thermodynamic temperature scale value to be more accurate or to be more acceptable other than the degree Celsius scale calculation. বুঝা গেছে কি মানে নন লিনিয়ারিটি কেসটা কোথা থেকে আসলো?
Yes, sir.
Yep.
Achha, let's look at question number B. Have a look at this one. This is a simple problem, but we have a lot of numbers to work with, and it's a 4-mark question, so might as well take some consideration. A polystyrene cup contains a mass of 95 grams of water at 28 degrees Celsius. A cube of ice of mass 12 grams is put into the water. Initially, the ice is at 0 degrees Celsius. The water of specific heat capacity 4.2 × 10⁻³ joule per kg per Kelvin is stirred until all the ice melts. Assuming that the cup has negligible mass and that there is no heat exchange with the atmosphere, calculate the final temperature of the water. Achha, সিচুয়েশনটা বুঝো। একটা পলিস্টাইরিন কাপের মধ্যে 95 গ্রাম ওয়াটার আছে, so I might as well prefer to draw that. Let me remove this whole thing elsewhere. So try to visualize this thing. We have a polystyrene cup within which we have about 95 grams of water at 28 degrees Celsius. So 95 gram water starting at 28 degrees Celsius. We're gonna drop a cube of ice which has a mass of 12 grams, and initially the ice is at 0 degrees Celsius, which means it is about to melt. It's at the transition temperature, it's at the melting point. And we're gonna initiate a cube of ice or mass of ice. This much is put into the water. Initially, the ice is at 0 degrees Celsius. The water of specific capacity 4.2 × 10⁻³ joule per kg per Kelvin is stirred until all the ice melts. So we dropped it over here, and then we kept on stirring until all the ice is melt. So ultimately, the ice will melt. In the process of the ice melt, this water would become somewhat cooler. And then the temperature of this ice melt water, which is supposed to be initially start at 0 degrees Celsius, just melt ice, that temperature is going to slowly increase and the temperature of the hot water is going to decrease. Eventually, they will come to an equilibrium. As long as the equilibrium is not reached at a much lower temperature, the temperature of the hot water, which was initially kept taken in the polystyrene cup, should keep on decreasing. The question says, assuming that the cup has negligible mass, because we are considering no heat loss should be happening with the cup, and that there is no heat exchange with the atmosphere, calculate the final temperature of the water. the specific latent heat of fusion of ice is this much. So we are asked to find out what should be the final temperature of the mixture. So what I need you to understand, or what you can actually visualize this problem in a lot of different ways as you want, but there is a certain specific way that I usually draw this thing. Let's say the cup mass was initially at 28 degrees Celsius. The ice was initially at 0 degrees Celsius ice. So what's going to happen in the process of 0 degrees Celsius ice melting into 0 degrees Celsius water? I'm showing this in a horizontal conversion because there is no temperature change, but there will be some heat absorbed as well. In this process, this temperature will drop a little bit. Let's say the temperature drops by this much. Then the 0 degrees Celsius water temperature will start rising, and this cooler water temperature is going to keep on falling because they're going to start exchanging heat. And eventually, this time they will finally reach to a point which is somewhere in between this temperature. So between 28 degrees Celsius and 0 degrees Celsius, there will be somewhat a halfway point at which the temperature will come to a steady value where the total heat exchange between the cold object and the hot object would be finished. Let's assume this temperature is theta degree Celsius. The question is asking us to find out that number. It goes to the information. So what we need to understand is that for the water to drop from 20, for the hot water to drop from 20 degrees Celsius to 30 degrees Celsius, there will be temperature change, but no state change. So we are going to go for AMC delta theta. For the ice to water melting, we have a state change. So we're going to go for M into LF, latent heat of fusion for this part. And for this much part, we're once again going to go for MC delta theta. But what you need to understand that all of these MC here in this case are not equal. This was for the polystyrene cup mass, which is 95 gram. And all of this mass for this lower part is for the ice mass, which is 12 gram. So let's try and solve this math with all the numbers that we have available. If I was doing this math, I could do it this way. Let's say I'm going to write Q given equals to Q taken. That is also a hot object absorbs it, the cold object absorbed. I have to write that the unknown temperature is 30 Celsius. I should have written this on the top. So let me use let final temperature is theta degrees Celsius. So then this equation should work. Absorbed heat from by the ice melting and the ice melted water heating up. So this is gonna be all of these constants are given in joule per kg by Kelvin, but the mass are given in gram. So 0. What is the mass of the ice? 12 gram. 0.012 into if you I'm actually have a bit of a difficulty to write directly the numbers because I didn't write the equation. So I would definitely appreciate even as an examiner that you write the equations MLF plus MC theta minus 0 should be equals to MC 28 minus theta. This is just showing that we are going to use this two equation, and then you can slowly start applying these numbers. So 0.012 multiplied by 3.3 into 10 to the power 5 plus plus 0.012 multiplied by C, which is 4.2 10 to the 3 multiplied by theta, this much should be equals to, so might as well wrap this one, should be equals to 0.095 multiplied by 4.2 into 10 to the power 3 into 28 minus theta. সো এই হচ্ছে আমাদের থার্মোডাইনামিক ইকুয়েশন। আমরা চাইলে এই ভ্যালুগুলো আলাদা আলাদা করে ক্যালকুলেট করতে পারতাম, বাট আই প্রেফার টু রাইট দেম ইন এ সিঙ্গল লাইন বিকজ দ্যাট অ্যাকচুয়ালি really reduces the amount of writing that you actually have to do. So let's try and go ahead and calculate out how much would be this theta value. এই ইকুয়েশনটা বললাম খাতায় একটু লিখো সবাই, লিখে আস্তে আস্তে ক্যালকুলেট করে বাই করো যে থিটার আলটিমেট ফাইনাল ভ্যালুটা কি হবে। It might take some time because it's a bulky calculation, so you might have to write a few more steps over here. You might, but not writing them is not a big deal, but showing some calculation always pleases the examiner by a whole lot. But before I give you some time to actually do the calculation, এই ডিসকাশনটাকে বোঝা গেছে about the equilibrium temperature? Did it make sense?
Yes, sir.
Yes, sir.
ঠিক আছে, এই ক্যালকুলেশনটা করো, করে থিটা ভ্যালুটা বাই করো। আমি একটা জিনিস নিয়ে আসতেছি, জাস্ট আ সেকেন্ড। কত আসছে থিটার ভ্যালু?
Sir, calculate করছি এখন।
ঠিক আছে, করো।
Sir, 16 আসে।
দেখো মার্কস স্কিমের সাথে ম্যাচ হয়েছে কিনা, মার্কস স্কিমের এক্সামিনেশন রিপোর্টটা একটু দেখো।
Yes, sir. 16 আসে।
ও ইয়া, কোচিং বুকলেট আছে, গেলে পাওয়া যাবে। জাস্ট গট দ্য রিপ্লাই।
স্যার
জি বাবা।
স্যার আমরা কি রুটিন নিয়ে এখন কথা বলতে পারি? বিকজ 2:30 বাজে না, সাদিয়ার আরেকটা ক্লাস আছে, তো ও পরের কথা
হ্যাঁ
বলতে
হ্যাঁ হ্যাঁ,
পারবে না।
আমি রুটিন নিয়ে আলাপ করবো, যে রুটিন নিয়ে আলাপ করার জন্য রুটিনে জিনিসপত্র লিখতেছি। So we solve this problem. এটা আনসার ম্যাচ হয়েছিল।
ইয়েস স্যার।
আচ্ছা, এই ক্যালকুলেশন গুলো অ্যাকচুয়ালি ডিফিকাল্ট না, বাট অনেকগুলো নাম্বার নিয়ে একসাথে কাজ করতে হয়, সো ক্যালকুলেশনটা করার সময় ভুল হতে পারে। জাস্ট ডু এক্সট্রা স্টেপস ইফ ইউ নিড, অ্যান্ড বিয়ার উইথ দ্য স্টেপস স্লোলি, যাতে করে ক্যালকুলেশন ভুল না হয়। এই ক্যালকুলেশনটা একটু মেটিকুলাস দেখে এই প্র্যাকটিক্যালি এই কোশ্চেনটাতে 4 মার্কস দেওয়া আছে। So just because the calculation is large, it's a worthy mark, but the actual theoretical concept is actually really simple, that heat energy would be given up and absorbed by equal number of particles. Acha, question number 10 is actually quite simple. 11, 11 is also quite simple. I'd say yes, we have the pressure, we have the volume, we have the temperature. We are asked to calculate the total amount of gas in mole for the container. So you have to do the calculation individually, differently for both of these containers. So A mole number আলাদা বের করতে হবে, B এর mole number আলাদা বের করতে হবে, তারপর দুটাকে আবার অ্যাড করে দিলে total mole number of gas বের হবে. So it's not so difficult. আচ্ছা, নাম্বার 12 তে একটু খেয়াল করি, এখানে ওয়ার্ডিং এর জন্য মাঝে মাঝে ভুল হয়। 12 এ বলছে হচ্ছে the first of thermodynamics may be expressed in the form delta U equals to Q plus W. So here the change in internal energy, or to be more precise, increase in internal energy is given on the left side, which should mean that Q should be the input heat, W should be the input work. Explain the symbols in this expression. So if I was answering this question, I would write this way: increase in internal energy of the system plus Q, heat supplied into the system, W, work done on the system. So be careful about the prepositions because that's what's important. Then we have a question: state what is meant by specific latent heat. We have 3 marks into this question. So this is basically a state question, but we have 3 marks into it. So what should be the 3 mark can be scored for? First of all, the definition of latent heat is very simple. It is the amount of energy required per mass, per kilogram of an object, and that's the idea. But the additional information is that in this process the temperature remains constant. That's what is important for latent heat of fusion. I mean, whenever we use the term latent heat, it is always measured when the temperature is stuck at the transition temperature, the solid to liquid or liquid to gas. So that's a bit important information. Still, because it's a 3-mark question, I'm going to have a look at the mark scheme and find out what does the mark scheme has to tell us. Number 12, it says that thermal energy required to change the state of a substance per unit mass. So energy required per unit mass, এইটুকু হচ্ছে 1 mark. 2 mark without any change of temperature, which is the precondition, is the 3rd mark. If we look at the examiner's report, most answers did not make reference to change of state rather than specify either fusion or vaporization. So the examiners were looking for change of state for a more general expression, not the word exclusive word melting or vaporization, because they have only used the term specific latent heat. They didn't say specific latent heat of vaporization or fusion. They didn't say that. So other than writing a single word referring to either the change of solid to liquid or liquid to gas exclusively, the examiners appreciated if you made it a bit more general and wrote it in terms of change the state of substance. Then comes per unit mass and without the change of temperature. And then it says consequently comparison was not made. Sorry, candidates should be advised that in definitions where a ratio is involved, then this aspect should be made clear. Candidates should be advised that in definitions where a ratio is involved, then this aspect should be made clear. Reference should be made per unit mass rather than either of a unit mass or of 1 kilogram. Okay, using the word par is emphasized in this part. So rather than if you write that the amount of energy required to increase to melt one or to melt unit kg, other than writing that, because there's a division involved, they emphasize on the word par, so that the division operation is more importantly highlighted within the answer. Simple question, but then again, whenever a definition has 3 marks in it, I prefer to look into it, that what these 3 marks are for, because sometimes you might feel that you don't know enough to score full 3 marks. In number 2, it says use the first law of thermodynamics to explain why the specific latent heat of vaporization is greater than the specific latent heat of fusion for a particular substance. So important information. Have a look. Why the fusion specific latent heat of fusion should what the specific latent heat of vaporization is greater than the specific latent heat of fusion for a particular substance. So simply going, we can consider the example for water or ice melting into water and then liquid water boiling into vapor. We are not going to write in terms of water, but for the sake of visualization, you can consider those substances which can work pretty well. The reason boiling always takes significantly more energy compared to melting is because in the process of boiling, we have to completely overcome the intermolecular attraction forces between the substance particles so that they become completely free of each other. And that's one part of the energy we have to feed for. The other, another significant portion of energy is required whenever the boiling process occur. The gaseous substance particles, which were just created from the liquid state, they have to occupy some volume of their own within the atmosphere by pushing out the atmospheric particles. That's also a really important cause, that because the particles have to physically move out, atmospheric particles, to make their own space within the atmosphere, that pushing out on the atmosphere also requires some energy in terms of work, which also has to be fed within the boiling process of vaporization. Whereas in the fusion process, we only have to give enough energy so the particles can break free from their fixed three-dimensional structure by partially overcoming. You can use the word partially overcoming, or you can like by loosening up, or by having a significant decrease in their intermolecular attraction force, but not completely overcoming it. So in the process of boiling, the intermolecular attraction force is entirely overcome, so that individual molecules of the object or of the substance are totally separate from each other. So you really have to give enough amount of energy so that all the particles are completely separated from each other. Whereas for the solid to liquid conversion, we just have to weaken the force enough so that they break free from their fixed three-dimensional lattice structure. The Mark scheme says over here that when evaporating, greater change of separation of atoms or molecules, greater change in volume, identifies each correctly with delta U and W. Okay, so I actually said the whole process by general terms, but I did not use the first law of thermodynamics. Okay, I messed up this part. I said what's going to be happening, but I did not use the first law of thermodynamics. I mean, I put no regard to this phrase. I forgot about this. So I'm definitely not going to score the 3rd mark of this question. So if I'm trying, if we have to write this answer in terms of the first law of thermodynamics, for the case of boiling, heat energy would be absorbed to overcome the intermolecular attraction force, and also heat energy should be also required because work will be leaving from the system. So for the case of the evaporation, W would be minus. From this equation, W would be negative, because this W over here for the first of thermodynamics expression is actually defined as the work done on the system, where physical work gets in the system from an external source. But when the boiling will happen, evaporated molecules would have to push out atmospheric particles. Thus, work has to leave from the system. So W should be negative and Q should be pretty large, and there should be some delta U because there is obvious state change. Particles are overcoming their intermolecular attraction force completely. So that needs to be specified in terms of these terms. They didn't specify exactly how you should utilize those things. They just said identifies each difference correctly with delta U and W and blah blah blah. So then it says that for most answers given, it was carried because the question had not been read carefully and consequently a comparison was not made between the two changes of state. For example, many candidates stated that the volume change on evaporation is very large, but then did not mention volume change on melting. Likewise, the difference between the changes in the separation of the molecules, the difference between the nature of the bonds was not discussed. Other statements